Okay, so what we want to look at in this section is continuity, like where graphs are continuous and discontinuous, where do they stream together seamlessly, and where do they have open places, holes, leaps, jumps, asymptotes. Those are places where we're going to be discontinuous. And if I ask you about this graph right here, you'll notice that we are going to be continuous everywhere that we don't have a hole or a jump. So I'll just highlight real quick places where we're continuous. From this solid circle around to this guy right here. From this open circle to this guy all the way around to this. From the open circle all the way around to that endpoint. So these are places where we are continuous. We are discontinuous right here. This is a point of discontinuity. And we're discontinuous right here. This is also a point of discontinuity. Okay? Both of these are jump discontinuities. And so what we do to determine continuity is we look at the limit as we approach some interior point. And if we're continuous, then we have a limit on the interior point, and at that limit we have a specific number that matches. So in other words, if we look at the function, something easy like say f of x equals 2x plus 3, and I want to know what's going on as x approaches 2, then I can put 2 in for that x, and it becomes the same thing as f of 2. And if the limit is the same thing as f of 2, which in this case is 7, then I am continuous. It's continuous at an endpoint if the function equals an endpoint from approaching the correct way. So if I look at like as x approaches a from the positive side, that would be like on this guy right here. This is an endpoint where we're continuous all the way to that endpoint. Because if I look at that function at that spot, if I look at f of 2, do I get that function at that same limit? And these are easier to see when you dig into problems, but notice the difference between this function right here and that open hole right there. That is not continuous, because as you come in from the right, we go to a place where we can't define our function at that specific point. The same thing as you're coming in from the left. This guy right here is continuous, because we are defined at that point, and this spot right here is discontinuous because we are not defined at that point. So that's how you look at continuity on endpoints. By the way, for another endpoint, we are discontinuous here, we are not continuous, and we are continuous here. So those are your ways that you look for continuity. And to go with all those different continuities or discontinuities inside of functions, there are different ways to describe them. For example, if I can take one point and plug one point into my function where there's a hole, this is called a removable discontinuity. All it takes is being defined in one specific y value, and I complete the graph and make it continuous. That's called removable. Anytime you get anything around an asymptote, around an asymptote at all, this would be what's called an infinite discontinuity, because it goes to infinity. We're going to look at some functions that do some really wacky things, and if it looks like this, where they just bounce, and no matter what you do, it's still bouncing, no matter where you look, it's still bouncing, this is an oscillating discontinuity, and we actually cannot take a limit with this oscillating discontinuity. And if you think of the good old Winter Olympics, where you jump to the next one, this would be a jump discontinuity. And you see these a lot in different piecewise functions and in the greatest integer function. So all of these guys can creep up at different times, but these are basically your 4 different types of discontinuity. So when we're looking at all these different continuities, there's one of the things that we can talk about that's maybe just a little bit confusing, and that is identifying continuous functions. So a function is continuous if and only if it is continuous at every point of its domain. And so the key phrase here is every point of its domain, because what happens is a lot of things that we would say are discontinuous are actually continuous functions. A continuous function does not need to be continuous over its entire interval. For example, y equals 1 over x. Y equals 1 over x. This is a continuous function because it is defined for every point in its domain. Okay? What number is not in the domain here? 0. X cannot be 0. That's the only place we have an asymptote. And since that's the only place we have an asymptote, then that's the only place that we're discontinuous. And if that's the only place that we're discontinuous, since 0 is not in the domain, the function is continuous. Okay? So the key thing, the key phrase, the key part of the world here that we need to understand with these types of questions is, are you continuous over the entire domain? And if the answer is yes, then it is a continuous function. Okay, so that leads us now to a thing called the intermediate value theorem. And you're actually going to see this later in calculus, but we can talk about it right now with continuous functions. Remember, a continuous function means that you can start at one specific point, so we would call that point A. You stop at a specific point B, and when you create your graph, you never ever pick up your pencil, so you're continuous the whole way. So I would be continuous over this entire graph right here. I don't know what the function looks like, but I know it's continuous. I never picked my pencil up. So what the intermediate value theorem says is that there's some point in there, some random point, okay, that is going to be equal to k. Okay, so when I put some random value in, I get a y value out. Then so what we're saying is, if I have a y value at this point right here circled in red, whatever that y value is, and we're calling it k, then there has to be some point on the x-axis that when I put it into the function gives me that number. That's what the intermediate value theorem says. It says that for every y value that I find along this green line, I can find a corresponding value on x that when I plug it into the function gives me that y value. Okay, so here we go. Intermediate value word problem. So think about this. Is any real number exactly 1 less than its cube? Okay, so we got ourselves a word problem here. We've got some math that we're going to have to pay attention to. Is there any real number x that is exactly 1 less than its cube? In other words, can we solve this equation? Okay, so think about what we're graphing here. We're graphing the cube root function, and we're going to graph the cube root function that looks like, or not the cube root function, the cubing function. So let us move x over so we can have 0. All right, and it looks like this. So if you graph this on your calculator, you're going to get a graph that looks something like this. Okay, go ahead, graph it on your calculator. It'll look about like this. And if I were to put my numbers up here, this would be -1, this would be +1, -1, 1, 2. Somewhere between 1 and 2, I cross the x-axis, and that's the solution that I am interested in. So that means that there is some number right here that is exactly 1 less than its cube, and that's what the intermediate value theorem says. It's kind of a confusing looking thing, but when you really think about it, Does this blue line cross the x-axis at some point? And the answer is yes. And since the answer is yes, our intermediate value theorem for continuous functions works.